All right, hell yeah. So we have, engineering, mechanics, and dynamics. Now, this isn't a problem in a book. I just made it up myself. So we want to know how fast, if the Earth is spinning, you know what I mean, maybe you fly off. Well, we don't want to do that, but we want to weigh 1/6. We want the equator to feel like the moon. That would be pretty sweet. You could feel like you were on the moon. You would weigh 1/6 of your body weight right now. That'd be pretty wild. So I do like this Schwamm's outline. They do a really good job of taking the derivation. They start with position and then derive position. You know what I mean? First times the derivative of the second plus the second times the derivative of the first. Hey, you get an equation for velocity. Cool. So they do that same thing. Now they take the derivative of the velocity equation that gives you acceleration. And in doing so, man, you get a bunch of terms. You know what I mean? But at least they kind of simplify it down. And so we're not going to go through the derivation process. I'm pretty much confident in being able to do it, but there's just one little hiccup that gets me every time. So, but right here, so you have to get used to, like, if we do have a circle, you know what I mean? What we're doing is like, hey, we're going to be this little piece of mass on the outside of a circle, and the circle has some sort of radius. So now we get acceleration due to any one of these scenarios. So this is going to be acceleration in the radial direction. Hell yeah, we might get acceleration that way. And this is tangential. They use this phi, the angle phi. But then that's going to be acceleration in that direction. So this is tangential, and I guess you would call this the normal, kind of just the normal direction for acceleration. Okay, so what this says is if you're let's go to maybe this one first, because this is our radius. This says, hey, if our radius is changing with a constant velocity, cool. Then we'll get an acceleration. So now let's go to this one. This r double dot is the second derivative of the position vector, which gives you acceleration. You know what I mean? You take the position vector and then take the derivative twice, you get you get acceleration. So anyway, but what this says is like, hey, if you just are accelerating in this direction, so that's like a car going linearly down a road. You know what I mean? So in this radial direction, that is the linear direction. It'd just be like, hey, put this car on the road, and hey, are we accelerating? You know what I mean? So is our radius? So let's say we have this is our radius. Are we going to be in a fraction of time? Let's say we got a stop sign. You know what I mean? And then so in 1 second we're here, in another second we're here, and then in another second we're there, and hell yeah, now we're just getting up to speed. Well, look, like we had velocities, we had zero velocity right here, maybe just a little bit more right there, but you can definitely see, like even at this point, if we had some sort of velocity like 2 miles per hour. Well, if we had that constant velocity, in another second we'd be here, and then another second we'd be there. But that's not what we see. We see we're there, and we're making these big jumps. So we know that we have some sort of acceleration. You know what I mean? And in just the fact that our velocity would be 0, and then it would be something else, shows that you have a change in velocity. That's the definition of acceleration: is change in velocity, change in time. dv dt. Cool. So this one's pretty straightforward. It's just like, hey, our radius is accelerating, and then this one's pretty straightforward too, because this is radians per second per second. You know what I mean? Just like you got 3 things with radians. You know what I mean? 1 radian is about 60 degrees. So hell yeah, that's going to be 1 radian, approximately 60 degrees. It's 57.3 degrees. And if this was the radius, take a string and then just drape it around the circle, you'll get to there. And do that 6 times, you'll basically get around. It's 6.28 or 2 pi radians for a full circle. Cool. So what we want to see, what the hell do we want? Oh yeah, this angular velocity. So radians are just a bugger to work with. So I always say, hey, radians times radius is something normal. And if we're just saying, hey, this angle of 1 radians, so we got 1 radian times the radius. Well, let's say it's just 1 meter. Well, guess what? This arc length is 1 meter. Cool. And now if we have an omega of 1 radian per second, so now you'd be like, hey, we're going around a circle, but now we're going to be like 0, 1, 2, 3. It's about 6 seconds to get around a circle. That's 1 radians per second. Sweet. So if we take that radians per second times radius, you know what I mean, that gives us something normal. And this gives us our tangential velocity. So that's cool. And then so this is omega r is equal to tangential velocity. But if we do radians per second, and if you write it like this, hey, this is the change in change in velocity, change in time. It's the change in the angular velocity, you know, change in t. And this is going to be alpha. This is radians per second. It's angular acceleration. So we're going to say angular acceleration times radius. That gives us something normal. And that just is the acceleration in the tangential direction. So that's pretty cool. This is just acceleration tangential. This is just acceleration normal. You know what I mean? So those are the two. Like if you're going to start a saw, it is going to maybe go like 6,000 rounds per minute, but it's going to take about maybe 1 second, or maybe about 1 second to get up to 6,000 rounds per minute. So the average acceleration in that time, it goes from 0 rounds per minute to 6,000 rounds per minute. Well, now you have angular acceleration. And if we're saying it goes 6,000 rounds, like how many radians are in 1 round? Well, you have about 6. So this would be 6,000 times 6 radians per minute, and then that's a lot per minute, but we'd have to divide by 60 to get the radians per second. You know what I mean? So this would be 100 times 6, so it would be 600. And let's check that, you know what I mean? So if we have let's do factor label method on that. So we have 6,000 revolutions. I'm just going to go revolutions per minute. I'm saying that in 1 revolution has 2 pi radians, so 1 circle. And I'm going to say 1 minute is 60 seconds. So minutes cancel, revolutions cancel, and we're left with radians per second. Okay, so we're going to have 6,000. And did I do this? Yeah. So yes, just 6,000 revolutions. What is that in radians per second? That's what we're doing. So 6,000 times 2 times pi divided by 60. Okay, hell yeah. So that's 628 radians per second. So that's kind of a little check on reality. We guessed 600. Cool, but now what's the angular acceleration? If your saw does take 1 second to start, you'd have to clock it, you know what I mean? And it's not going to be, this is going to give you an average, you know, it might get up to, 4,000 radians in 1/10 of a second, and then take 0.9 seconds to get that extra, it's not going to be consistent probably, or it's not going to be a constant acceleration, but we can figure out what the alpha is by saying that this is the change in omega, change in t. So it's d omega dt. It's the change in angular velocity. So this is really hard to say these words, but yeah. So you have angular velocity, and your change is 628.3 radians minus 0. So we went from 0 to 628. Anytime you do a change, you do the second minus the first. Okay, and then the change in time, same thing, is going to be 1 second minus 0. Second minus the first. So we're going to have an angular acceleration of 628.3 radians per second. You know what I mean? So that's our angular acceleration in that case. Hell yeah. So now, and then this one is if you just have your radius just has a velocity. So I consider this like, hey, there's like near the equator, there's one of the buildings that it has like the fastest elevator. You know what I mean? So hey, your radius from the center of the Earth, you're gonna go on that elevator. It's gonna have a constant velocity from bottom to the top. And so, hey, this is going to apply, and you're going to feel an acceleration in this direction. You know what I mean? So if you're up against the wall, you're going to feel a little bit. And you're not. It's like eyelashes. You know what I mean? It's alright, bummer, my camera cut out. But yeah, you just won't feel anything going up that elevator. You know what I mean? You'll feel like grams. You know, grams of pressure on the back. You know, if you stood up against the elevator in the right direction. Anyway, so what we're going to do is we're going to show that now we're going to get, so that was this one. Now we're going to get into this one. And this is the main player for why things fling off an Earth. You know what I mean? If you're at the equator, you're getting flung off the Earth. If you're at the North Pole, you know, you're just standing, you know, just on top and you're just going in a circle. You're not getting flung off. So it's very similar to like a merry-go-round. You know what I mean? Like, you have to hang on for dear life. So even at the equator, you're sacrificing your own weight to stay on the ride of the Earth. But the Earth spins so slow, like it's just ounces. Like at most, you might weigh 8 ounces less at the equator. But yeah, that would be a separate problem. But what we want to know is how fast does the Earth have to spin where it does kind of turn into a moon scenario. And that's this equation right here. And so I think we did it. You know what I mean? This one's kind of mysterious with the elevator at the Earth, you know, having a constant velocity. Obviously, it's not that big of a deal. The acceleration is super tiny, even for the fastest elevator. You know what I mean? But some problems that have a smaller radius and that you're moving radially, you know, that's where this comes in. And we could talk about that one, but we're not going to talk about that one. And I consider this one kind of the mysterious one. You're like, well, how does that work? Well, this one, just in a nutshell, is like when you are spinning around the Earth, like, hey, like you're spinning with the Earth, but then if you're going up, well, like okay, so you're spinning like this fast tangentially, but the top of this ride is spinning hella faster. And the fact that you just move up the elevator, means that you have to move hella faster too. And to do that, you get a change in velocity in that direction. You know what I mean? And change in velocity, change in time must be an acceleration in that direction. So that's going to be very similar to what's happening with just getting kind of flung off. And so here's kind of the example that I use is if you are like on the Earth, or if you're spinning around a big circle, like if you're not connected, if you just let go of this ride of the Earth, you know what I mean? Hey, you just want to go in that direction. So your velocity, you know, is basically tangential. You know what I mean? Anytime, so this is synonymous with if you have a string and then you have a mass and then you're spinning around. This is the same thing. Like we are a mass, and this string connected to the center of the Earth, we have to hold on about 8 ounces. You know, 8 ounces of tension on that string to hang on to the ride of the Earth. But if we cut that string, heck yeah, we're going to be going that way. And at the equator, we're going like 1,000 miles per hour. You know what I mean? That's pretty wicked. So if we cut that string, you know, we're going to be going 1,000 miles in that direction. Okay, so where this comes into play is like right now, all of our velocity is just tangential when we're at the equator spinning. None of our velocity, you could say that we are not moving towards the center of the Earth. I think we would all agree with that. Like, hey, at any one given point in time, if I'm on the equator, I'm definitely moving 1,000 miles per hour tangentially, but I am not moving towards the equator. But then you take this, so what we're going to do is we're going to take a small change in time. So here's the center of the Earth, here's us, and we do have some sort of radius. So we're just going to take the tiniest sliver, you know what I mean? Maybe like 1 second of time. And we should have been here. And I should make this just a little bit. So we're going to be on this arc here. Tangentially, we want to just go straight. You know what I mean? So our velocity is going that way. Velocity tangential. So in 1 second we should be here, but we're not. And at this point, again, we don't have any velocity towards the center. So just based on the principle of like I should have been here if I was moving in a tangential line, but I'm not there. I'm over here. So then I must have had, at some point, I must have had some sort of velocity towards the center of the Earth. I must have had some sort of radial velocity. But what we do know from this point, we're fixed, we're stuck. We have our velocity radial is 0. So then what you do is you're like, well, what is the distance here? Because if we knew the distance here, and this sweep of time was 1 second, so we're going to say our change in time was 1 second, then we would know that we had to, and there's two concepts here. So in that 1 second, we had to move from there to there. So you get this, and don't confuse the two, but this is velocity average. The velocity average is going to be, velocity is units on it as meters per second, always good, because now we can say, hey, the units are the equation, so we're going to say this velocity average is that distance over that time. So velocity just in general is change in position, change in time, and we see that we went that distance d in 1 second. Cool, that's our average velocity, but we didn't have any velocity right here. So just spelled out, this has to be, this point right here, we have a V max of 2 times this. So our V max is 2 times that distance in 1 second. So it's twice the velocity average. Okay, so hell yeah. And then we can actually put some numbers on this. And so we're going to do that right now. So the radius of the Earth is just a good one to know. It's 6.37 times 10 to the 6. It's 6 million. It's 6 million meters. You know what I mean? Now this is a tricky one. You know what I mean? One revolution of the Earth in 1 day is not 24 hours. If you used it, cool. But it's minus 4 minutes. You know what I mean? And it's actually like minus. Yeah, that's all I know. I can't get too much more specific than that. But what we're going to have is 23 hours, 56 minutes, and, maybe 4 seconds. Maybe I do remember that. I don't know. Maybe it's 9 seconds. Forget it. That part is just who cares. But we do know that one day is 4 minutes less. Because if we have 365 days, and each day is 4 minutes less, we're going to have 365 times 4 times 60, and that's going to be divided by 3,600, and that's going to be 24 hours. So every year, what that just says is the Earth actually rotates 366 times in 1 year. And the reason is if you have the sun over here and you have the Earth right here, I do a pretty good job of this. Like here's high noon right there, and then so when we rotate once, we're back to here. But guess what? Yeah, if we didn't rotate around the sun, yeah, it would be 24 hours. We know that because it would be less. If we didn't rotate around the sun, we would see every day would be 23 hours 56 minutes. But what happens is so we're horizontal with the sun, and when we rotate, it takes 23 hours 56 minutes to do this. But then we're also going around the sun. So even if I'm up here, now I'm not facing the sun anymore, and I have to rotate an extra 6 minutes to face the sun. Now same thing, day number 2. I rotate, and now I'm faced this way, but hey, I went from here and then went up here. And then so I had to rotate again. So if I'm just fixed in position and rotate around the Earth like this, well, I have to rotate more to face the Earth. So hell yeah. So that's kind of where that comes in. All right, and what the hell are we trying to find? Like maybe arc length? You know what I mean? Like isn't that what we said? Like if we could find I have no idea what we're going to find. But anyway, so we're going to get this value in seconds. So we're going to go 23 hours times 60. That's going to be that many minutes plus that 56 minutes times 60. Cool, I'm going to store this as alpha t. So this is the time, 86,160 seconds for one rotation of a day. And maybe I do need to want to know what the circumference of the Earth is in meters. Well, that's just going to be 2 pi times the radius. That's going to be 2 pi times that 6.37 times 10 to the 6 meters. And let's throw that into our calculator. 2 pi 6.37 times 10 to the 6. And so there's our circumference. So now we have this many meters. We have like a hell of a lot. We got like 40 million. Meters, and we're gonna cover that many meters in 86,160 seconds. So now we're gonna say, hey, in 1 second, how many meters do we go? So we have tangential velocity. I mean, the velocity tangential is this many meters in that many seconds. So it's the distance all the way around the Earth, and we're doing that in this many seconds. So we got alpha c divided by alpha c divided by alpha t, and now we have a speed of 464.5 meters per second. Now this is in meters per second. I like to go times 2 for miles per hour, and if you can remember like a 25% tip, you know what I mean? Hey, you get pretty darn close. So it's 1,045 miles per hour. Now, this is just a guesstimate, but this is right on. This is your tangential speed at the equator. Okay, so if this is our speed, if we can go 464.5 meters in 1 second, or meters per second, yeah, if we in 1 second we go 464.5 meters. So cool. So right now we're going to be going. Let's see. So yeah. So this arc length I'm going to call S is going to be 464.5 meters. And so now what we want to know is well, can we do this yet? We need to know this angle. You know what I mean? So now we just have a hella thin triangle. And I'm going to say, hey, this sweeps up in an arc like that. But now I'm going to bring it down right there. And I'm going to say that this radius, this is the radius of the Earth. Yeah, we didn't even need to figure out this arc length. But this was the radius of the Earth. That's going to be our hypotenuse, the bigger number. This is going to be our angle. Now, what is the angle in 1 second? You know what I mean? Because we have 360 degrees. That's going to be synonymous with this 86,160 seconds. So in one, we get 360 degrees for every 86,000. So we do 360 divided by 86. Holy hell. Sometimes. So let's say I did find the angle in degrees. You know what I mean? And then and that's going to be degrees per 1 second. That's kind of what we're trying to find. And how would I turn this into and then if I divided by holy Toledo. So once I get this, that's going to be degrees per second. If I wanted to get seconds, then I would invert it, and I would go 1 second per degree, and then I would multiply by 360 degrees. I don't know. Sometimes like just the simplest stuff can really bother me. You know what I mean? But hell yeah. So if I had this term of degrees per second, that's kind of what we want. Well, we have degrees, the degree sweep in 1 second, and if I inverted that and then multiplied by 360. I would get the number of second. I would get this 86. So this would equal 86160 seconds. So now I know that if I do 86160 divided by this 360, and then I invert that number, hell yeah, that's going to be the angle. So that's kind of a bizarre way to do it. But, you know, sometimes for the life of me, you're just like, well, isn't it just 360 divided by 86160? And hell yeah, it is. But that was just a little check on reality. You know what I mean? Right there, I kind of got stumped. It's like, well, isn't this angle just 360 divided by... Oh yeah, and here's why. Well, I can't even tell you why. Oh, whoa. Yeah. It's this number. This number is written wrong. So we need to write 860, 86,166 seconds per 360 degrees of rotation. That is the value right there. So even and that makes more sense. Big number on top, small number on bottom. It's the seconds that requires for 360 degrees of rotation. Now, like how do we just get 1 degree? Well, we want to you basically just invert it, but you can take this and say, well, I have 1 second, so I have units of seconds and units of seconds. So I definitely need to either divide by 1 second. And if I did that, you know what I mean? You can do anything you want with factor label as long as you don't mess it up. No, I'm joking. But like I could do this. I could say, hey, in 1 second, well, now I get inverted degrees. You know what I mean? So I get degrees inverted. You know, some number of degrees inverted, and then I would have to get degrees, I would have to take this and then invert it. So obviously, I would want to take 360 degrees divided by 86,160 seconds, and then multiply it by 1 second. Now, I have a factor label method that will get me degrees. So that was the whole roundabout way of just saying 360 divided by 86160. But sometimes those little things will help you when crap gets more complicated and you might not know the relationship between the two values you're trying to work with. Okay, so we have our angle. I'm going to store that as alpha or as theta. And now we just have like a big triangle. And again, what we're trying to find is basically this distance. Because once we find that distance, we'll know what's our change in velocity, or what's our velocity max. And if we can find this velocity max, we know that our change in velocity is velocity max minus 0. You know what I mean? It's the second minus the first over the change in time. That's 1 minus 0. We did this in 1 second. So technically, we changed our velocity from 0 to 0 max in this 1 second. And we don't know what this velocity max is until we find this distance change. Like, hey, in 1 second, yeah, we know that we should be moving tangential, but how much closer, you know, to the center of the Earth did I get? If you're thinking about it that way, well, let's see. Or I mean, it would be like this. If you had the Earth and we know that we're just moving tangentially, you know what I mean? And in 1 second we're out here, well, how much did the Earth fall away from us? You know what I mean? That's the question. Is like, how much is the Earth falling away from our feet every second? And it's pretty darn small. You know, I was kind of unimpressed. But no, it's just kind of fascinating. Okay, let's do it. So we have our triangle, we have our hypotenuse, and if we found this distance, we would be money, because then and totally just by let's see. So yeah, we're saying, because I'm also saying that this is the radius too. So this whole thing is the radius. But now at this point, I'm saying that this is the radius and this is my right triangle. So now we're going to find this is the hypotenuse times the cosine of the angle. Because here's our angle. The sun is shining on the sine part. This has to be the cosine part. Always take the bigger number, the hypotenuse, multiply it by cosine, or sine to get that one. But it's always a smaller number. Sine and cosine, always a smaller number. Multiply by the bigger number. Hell yeah, it gets you that. Gets you that component, you know what I mean? And so, hell yeah. So we're going to have the radius of the Earth, cosine of that angle. And that just gets us this distance, but to get the difference here, this distance, then we got to say the radius of the Earth minus that answer. So at the end of the day, that distance d is the radius of the Earth minus the radius of the Earth cosine theta. And you can shorten that to be distance d is radius of the Earth 1 minus cosine theta. You know what I mean? Want to do it this way? Just so we're, hell yeah. Let's do it that way. So alpha r, 1 minus cosine, and we have theta stored, and we're in degrees. Cool. So now we have this distance d, which is really small. You know what I mean? It's really small. You know what I mean? That's all I can say. It seems like it should be bigger than that, though. But you know what I mean? So we're going to multiply by 1,000, and holy Toledo. Hopefully I didn't mess up. But yeah, we got the radius of the yeah, holy Toledo. I didn't store radius of the Earth. So 6 times 7, 3 times 10 to the 6. It's so fascinating that it's so hard to check for errors. Like the second you get an answer, you just assume it's going to be right, but then when an error does pop up, it messes with you because you're just then you just assume that value is really small. I've done this problem before. I know it's not meters, but it is yeah. So now we're going to store this radius in our calculator as r. So now let's do it. We're going to go alpha r cosine of our angle. And then so we have something very similar to 6 million, 6.7 million. And then we're going to take alpha r, which is that 6.7 million, minus our answer right here. And that's our d. And if we multiply by 1,000, we have 17 millimeters. So every second we move 17 millimeters and take this answer times 100. Is 2 centimeters. Basically, you know, we move less than an inch. Let's do this. 2.54. All right. So if we take this divided by 2.54 centimeters in an inch, heck yeah, we move less than 3/4 of an inch every second. The Earth is falling away from us 3/4 of an inch. Man, I mean, the Earth is so big and flat. We get it, you know. We get why there's flat earthers. It's flat, you know what I mean? It's very flat when you're on the surface, you know what I mean? It's very flat when you're on the surface. Okay, so so now we have that distance d. Hell yeah! And so we can store that if I can find it again, you know what I mean? And so we're gonna store that as oh damn it, we're gonna store that as our distance d. And now we can find d max. You know what I mean? It's just twice that. We can find our velocity max. So our velocity. So see how we had in 1 second we had to travel a distance of 0.01. So 17. So we had to go 0.017 meters per second. You know what I mean? This was our 17 millimeters. 1, 2, 3. Yeah, 17 millimeters. So why isn't our velocity just 17 millimeters? Well, because we're starting with 0 velocity towards the center. It's much like a spring. It's just the second you push into a spring, there's no force on the spring. You actually have to change the length of the spring to get force. And then if you do, and then you get some max force, you know, in that spring, well, you started with 0 and then got up to some max. You know what I mean? So you started with 0, got up to some max. So the average between the average force that you had to put into the spring, over the distance, you usually do that with energy, is just going to be the force max divided by 2. Same thing here with velocity. Velocity is going to increase linearly to this Vmax, so we basically get an average point of Vmax divided by 2. That's our average, but what we want to know is what our change in velocity is. Again, acceleration is change in velocity, change in time. So we have a change in velocity towards the center of the Earth, and that's going to be our Vmax, you know what I mean, in that 1 second. So we're going to have Vmax in 1 second, and that's going to give us our acceleration. So our acceleration is 0.036 meters per second, towards the center of the Earth. Cool. And so now that we have that, we have kind of learned why this term applies. Why do you get an acceleration towards the center of the Earth? And so, if this was moving faster, really fast, hey, then you had to travel that distance, but in a much shorter time. Well, let's say that same angle, and the Earth was spinning 1,000 times faster. So you would take 1,000th of a second, and that would be the time it took to travel that. You know what I mean? And then so your acceleration would obviously, but even if it was just, you would have to have 100 times faster to get this to some normal number. You know what I mean? If it was 3.6. The Earth would have to be spinning 100 times faster. So that's going to be our first check on reality, is to get an acceleration of 3.6. You would have to spin 100 times faster. And gravity is basically, or it's 9.8. You know what I mean? It's essentially 10. And so if we went 9.8 minus 3.6, we would have a gravity of 6.2. You know what I mean? So we still wouldn't feel 1/6 our weight. So now let's talk about, before we flip to a new sheet of paper, if we want the equator to feel like the moon, our acceleration is 9.8. And this is what's causing us to weigh. You know what I mean? Our force is equal to mass times that acceleration of gravity. So if we want the force to be 1/6 less, then we have to have the gravity be 1/6 less. Our mass, the atoms in us, won't change. And so now we have 9.8 divided by 6. So we need to get down to an acceleration of 1.633. And so heck yeah. And this is the bummer part. Like I'm so bad at like the directions, and but we can basically just say, hey, that acceleration is flinging you off. The weight of you and the Earth, that gravity is pulling you towards the Earth, and so we can basically say when 9.8 minus whatever this number should be, the acceleration. The normal acceleration needs to be 1.633. And so we got 9.8 minus that. And we need an acceleration of that to be 8.16. And hell yeah. So that's going to be kind of our next goal. So we have this r omega squared, and this is going to be our acceleration normal, and we're trying to make it 8.166. If we do that, it's spinning fast enough to make us weigh like we would be on the moon, like 1/6 the gravity. All right. So what is radians per second? Like I said, radians per second times radius is something normal, and that's the velocity. That's the tangential velocity. And yeah. And then so we can basically solve it right here. But I think, yeah, I think I'm going to be done with this one. But this was the take-home point. Is just like, hey, this is kind of a hidden acceleration. You're like, well, why are we why is our acceleration towards the center of the Earth? And I'm just bummed out right now, because it's just like, yeah, your acceleration is towards the center of the Earth. But I'm just going to say, is like, I'm so bad at, like, I'm just going to make the mistake of saying like the centrifugal forces, feel like they're forcing you the other direction. But you do have to sacrifice weight to stay on this ride. You know what I mean? Again, if we just go from that practical example of like, hey, if you're spinning around an Earth at the equator, you're getting flung off. And that is your acceleration component. You know what I mean? You figure out the signs in what direction they go. So hell yeah. So just from this equation, we can find the radians per second, the angular velocity we need, and that's going to be, so we're going to have this 8.166 divided by r, that's going to be omega squared, and then we can say 8.166 divided by the radius of the Earth, square root of that, and now we have our angular velocity of the Earth. So we got square root of that divided by the radius of the Earth. And so we have radians of 0.001 radians per second. Now, if we did the radians of the Earth, you know, I think it's like 10 to the negative 7. You know what I mean? It's really small. So this is, so now we need to figure out what the tangential velocity is. I guess we could do that. Like right now we could be like, hey, radians per second. We have radians per second. And then if we multiply by radius of the Earth, that gives us something normal, our tangential velocity. I'm going to store this as alpha W for radians. And we're going to multiply it by the radius of the Earth. And hell yeah, we're going 7,414 meters per second times 2.225. And that's approximately, and this is on the high end. I think it's literally like 2.23. You know what I mean? So, but it is good to have little ways to remember conversion factors. So then you can kind of dial it in. It helps your memorization skills. So yeah, we have like 6,500 miles per hour. Okay, but now we want to know the length of the day. Like how fast would a day be? You know what I mean? So if we have and I'm going to store this as our tangential velocity. And so these are, if we're going 7,414 meters per second, well, hey, we take the circumference of the Earth in meters. And so now we have meters and we have meters per second. So what would we do to both these to get seconds? Well, seconds is downstairs. So I guess we need to divide by this. So we would do meters divided by meters per second. And meters cancels and seconds is what we're left with. Alright, hell yeah. So home stretch. And this meters is the circumference. We have that stored in our calculator as alpha C. Quick way to figure out how big a number is, just divide by like 10 to the 6. So now we know that's 40 million, you know what I mean? And if you didn't know, you divide it by 10 to the 9 if you thought it was bigger. But no, it's only, you know what I mean? So that's how you can kind of do things. And so we have that circumference, and then we have our velocity tangential. So we're going to take alpha C in my calculator divided by alpha V. And heck yeah, so we get seconds, 5,398.7 seconds. You know what I mean? So now we need to figure out how many minutes and hours that is. So I'm going to go 60 seconds is 1 hour. So we can just do that first. Hey, we got 90. Yeah, obviously that's minutes. So we have 90 minutes. You know what I mean? So that's basically, that answers it. 90 minutes per day. We would have to have a 90-minute day. You know what I mean? So there you go. Because in hours is just going to be divide by 60 again, and we get 1.5 hours. So an hour and a half. So 1.5 hours. If the Earth could spin if the Earth could spin once in 90 minutes, if our day length was 90 minutes or an hour and a half. It would feel like the moon at the equator. So that does it. Moon at equator. Oh, bummer. Is equal to 90-minute day. Alright, hell yeah. You know what I mean? And again, I apologize for the whole thing of like, you know, not knowing the direction. Acceleration is towards the center, but it's just like, why get so heady? You know what I mean? If something's rotating, like the mass that is part of that rotating object is getting flung off. You know what I mean? So it must weigh less. And so that acceleration is in that direction. That's just the way I'm going to say it. But yeah, I'm definitely going to hone my skills. Every time I make a video where I'm just like, oh yeah, don't know that. You know what I mean? I can't explain very well the directions. Like, why is it towards the center? And what does that mean? You know what I mean? Because it's a difference. You know, we can talk about this. If you make an amusement park ride where you're having, you know, let's say it's like one of those like conical things where everyone's like riding, you know, sitting on, and then they get flung off. Well, sure, that's very similar to what we did. But then the other thing is, let's say you have a wall that's spinning, and now you're standing vertical up against the wall, and heck yeah, you know. So you have like the centrifugal force that's like pushing you outward, and that's the fictitious force. And it's just fascinating. Depending on what side of this wall you are on, is whether you're increasing your weight or sacrificing your weight. Because even if you're on the Earth and you're at the equator and you find like a tiny culvert that you can barely squeeze into, and that culvert is pressing you down into the ground, well, now your force, your weight has increased because you're getting pushed up against the wall of the Earth. You know what I mean? So it's there's two different things going on here, and it's very important whether you design an amusement park ride where you're on the inside like a roller coaster, or you're, for whatever reason, on the outside and you're sacrificing your weight to stay on the ride. Okay, I'm going to leave it at that, but thanks for joining me, and guess what? That's a video. Alright, heck yeah. So I just looked up the answer, and so we're wrong, you know what I mean? But we're not wrong by much, you know, and that's good. Because what, you know, the huge red flag that I should have picked up from the beginning, I mean, then at the very start of this whole thing, didn't we say, hey, if we have something rolling, it's going to have an omega, which is going to cause a tangential velocity, but then this thing is rolling, and so it itself is going to have a velocity. So you're going to have so at any point, you know what I mean? So if this is the velocity of it, you're going to have, hey, the tangential, you're going to have the velocity tangent. If you're at the top, which is the omega r, that's going to be your velocity tangent of just a rotating disk. But the fact that the disk is now rotating too, you're going to have to add that to it. So I did not realize that. And then so in our situation where we have this disk rotating this way to the left, when this thing is released and has a tangential velocity in that direction, well, it also has a component this way. So well, it seems like that would. No, it seems like we should have been fine. Oh, this is fascinating to me. Because all we wanted to know was the height above the ground. Oh, this is killing me. Because that's the only thing we're concerned with is the velocity in the y component. Because the velocity in the y component is the only component that can generate any height. It won't have anything to do with the fact that the circle is moving sideways. So I'm actually, well, let's go over the solution and see if we can. I mean, that's half the battle. It's like, can you actually take someone's solution and understand it? So here is so they're using a value of g of 10 meters per second. And maybe it's that. Maybe I am 100% right. They just used a different value of g. So at the end of the day, we got 0.5, and we're going to have, oh yeah, that is right. You know what I mean? Because they got an answer of pi divided by 6, and because so let's see, we have 0.5 plus pi divided by 6 divided by 10. Nope, that's going to give us a bigger answer. Okay, well let's see what they did. This will be fascinating. But the cool thing is heck yeah, they do have this equation for theta. So this is so fascinating to me. So if our angular acceleration is 2/3, the definition of angular acceleration is the same thing as the definition of acceleration, being change of velocity, change in t. This is change in omega, change in angular velocity, change in t. Now this is the equation. or you can be like, or you can say it's dw dt, and then you can separate variables. So now we're going to have dw dt is equal to 2/3, and then dw is equal to 2/3 dt, or dw is equal to alpha dt, and then we can integrate to get omega, or angular velocity, is alpha t plus angular velocity initial. You know what I mean? And then the same thing, we can say angular velocity is change in radians, change in time. And then separate variables, we get d theta is equal to w dt, integrate, and we get an equation for the angle as a function of time is 1/2 alpha t squared plus the initial radians per second squared plus the initial position, theta initial. So heck yeah, this is what you would get also plus theta initial. That's the only thing that's missing on here. But they're just taking theta initial to be 0. But the initial theta naught is also 0. And then so you just get 1/2, 2/3, and then square root of pi. So yeah, you get that pi third radians, which we know is an angle of 60 degrees. And then so cool. And then the angular velocity of the disk is well didn't we find that equation? Angular velocity of the disk. Yeah, so that was the position. That's cool. But we also have an equation for angular velocity of the disk. It's the initial plus the AT. And if you write it, it's better if you write it like this because it just matches the integration. When you write it backwards like that, I don't know if it's considered backwards. It's just a little bit more confusing because you wouldn't do the integration that way. You would have the 1/2 AT squared first, and then the initial angular velocity second. Okay, but then we get 2 square roots of pi third radians. Now is that what I got? Yeah, because we had 2/3. This was the angular acceleration times the time, which is square root of pi. So that is our change in omega. You know, we definitely have that down pat. Now our velocity. Oh, they're saying the velocity of the center of mass. Is that what they're saying? Velocity of the center of mass? Maybe not. They do have this picture. Velocity of the center of mass. So if this thing is spinning this way, starting at the bottom, going up to here, they just drew it backwards. I spun it this way. They're spinning it this way. So yeah, so this thing's going this way, and so this whole thing is going that way. So if you get the and if here's the center of the circle, and I guess is this circle just bummed up? I was saying that's the center. That's kind of hard to see, but yeah, obviously the center of the circle, velocity, the center of mass. That might be the only part that I might be confused on. Is no, I don't think so. So if you have a circle and it's rotating and it's on the ground, the velocity is 0. It has, like, so if this thing's rolling this way with a certain speed, the speed is the center of the circle. The center, like if you're traveling on a bike, 2 wheels, it's the center of your wheel that's actually your linear speed. This portion of your wheel is fixed to the ground. It actually is not moving. And this is your velocity center times 2. You know what I mean? And then so, and then we just want to know if the wheel is just in space and it's spinning at the same speed. So like right now we have some sort of omega. And if we have some sort of omega, our velocity tangent at any point is just omega times r. And so what we're saying is that oh shoot, yeah, that is interesting. Like I'm kind of losing my track But yeah, if you just have a wheel that's spinning the same speed as your bike, but it's not hitting the ground, the velocity of the wheel itself is omega times r. Huh. Yeah, I would think that the velocity of the center of mass is just half that then. Well, where am I getting that wrong? Because they're saying the velocity of the center of mass is omega r, just omega r. Oh, that's fascinating. Alright, so then let's move on. So they say, so at the moment it detaches the situation, then the velocity I'm going to take a pause and then kind of work through this.